Hello and welcome back, everybody. Today in geometry, we are going to look at something called inverse and identity for mapping, actually. So inverse and identity, those two are actually going to be a type of mapping, which we're going to figure out how they actually work out. Now, first, we're going to go ahead and I guess kind of give a definition for identity, and then we'll talk about inverse afterwards. So identity, the definition for it is that it is a mapping, and what's going to happen is whenever you use the identity mapping, it takes any point and always takes it back to the same position. So identity doesn't really move the point at all. So it actually just makes it stationary. So if you can kind of think of it as an analogy, let's say that you are going to have addition, right? The idea is that the zero, right, the number zero is going to be considered the additive identity because zero plus any number is going to be itself. Or if you're thinking about multiplication, 1 would then be the multiplicative identity because any number multiplied by 1 is always going to be itself then. So for any mapping that you have, we're going to go ahead and call S. Let's just say that you have a mapping. And then what I want to do is I want to apply this identity then. So if we're thinking about, like, say, the product from the last section, if I take any mapping we call S, and then we're going to multiply it or do a product with the identity, the result is that it's going to be the same thing as just using that mapping. And then afterwards, I'm going to use the identity, which is then just the same thing as saying, hey, we're just going to use the mapping itself, right? Identity doesn't literally do nothing to the point. So that's basically the idea behind it. Okay, so you're wondering, okay, well, what's the point of having this identity? Because it's kind of like useless, right? Because you're not doing anything to that point, but just saying that it's going back to itself. Well, it's because we need to use the identity as a definition to define what's an inverse then, okay? So here, let's now go ahead and define an inverse. So in the inverse, right, the inverse mapping is a mapping such that the following is true. So the inverse is going to be a mapping. We'll go ahead and call it B for right now. For another mapping, call it S, such that the mapping of S and B is going to be the same as the mapping of B then S, and then that is going to give us the identity then. The way that we denote it is that S is going to be equal to the inverse of B, so that's B to the negative 1, or S inverse is going to be equal to B. So the way you can think about it is that, hey, if you have a mapping that is going to be called S, right, then you're going to apply the mapping we'll call B. And if it's the case where if you apply S and then B, and that point P goes back to the original position, then those two are going to be inverses of each other. So in an analogy, the way you can think about it is that if you're using real numbers, right, every number is going to have some sort of inverse. So under addition, so for example, let's say that we have the number 4. The additive inverse of 4 is going to be negative 4 because 4 plus negative 4 is equal to 0, which is the identity, which is exactly what I have in this case. Whereas if I have the number 4, its multiplicative identity is going to be 1/4 because 4 times 1/4 is equal to 1, which is the multiplicative identity for, because 1 is the multiplicative identity, okay? All right, so let's go ahead and try to apply this so you can see how that actually works out. So let's say that we have the following then, okay? Let's start first with translation. Now, translation, we know that the definition of it is going to be T is defined as X comma Y, and then that's going to translate into something like, say, X minus A, and then we have Y minus B. So over there, let's just say that our translation is going to be the following then. Let me just go ahead and make it plus to make it a little bit easier. So over here, we have a translation. That tells me that I am going to move to the right by A, and then I'm going to move up by B. That's what this translation means. What I want to do is I want to find the inverse of this translation. I want to find the inverse of this translation. So the inverse, we first denote it as the following then. So it's like T to the power of negative 1. That means the inverse over here. So that's this guy right here. So the question is, okay, if I apply T to some point, what would I have to do then to get from that new point back to its original position? What do I have to do to get back to its original position? So let's say, for example, I am going to have 0, 0. Okay, so let's say 0, 0 is going to be the point, and my translation is going to be, I don't know, we're going to go ahead and take x, y, and we're going to go ahead and say x plus 3, comma, y plus 4. So the point 0, 0, if I applied the translation, we're going to go over by 3, and then we're going to go up by 4. So my new point right now is going to be at 3, comma 4. So I want to know from that new point, what would I have to do? What kind of translation would I have to do to get back to 0, 0? Well, you can probably see how that works out then. So my translation for the inverse is going to be x, y is going to be translated. Well, since we're going back to the original, then I'm probably going to have to subtract 3, right, for x. So it'll be x minus 3, and then it'll be y minus 4, because that will get me back to my original point. So that means that this is going to be my inverse then, because that takes me back to where I first started. So in conclusion, if I have x plus a, comma, y plus b, then the inverse of the translation is x minus a, comma, y minus b, because that'll take me back to wherever I started. When it comes to rotation, it's kind of the same idea, right? You take any point and then you rotate it about point O, and the result is going to be somewhere else. So let's say that point P is over here, and if I rotate it by point O right here, by a certain angle theta, then the result is going to be over here. So that's going to be P prime. Well, now I want to go from P prime back to P. So then that means I want to solve for what is the rotation inverse. Well, if we're going backwards, then the best way of looking at it is that we're just doing, well, the same thing, but except we're going in the opposite direction. So to me, then the rotation inverse is going to be, we're still going to use O as our center point, but this time we're going to use negative theta in order to get back into the original position then. So that right there is then going to be our inverse for rotation. And finally, for the last one, if I have a dilation, I want to go ahead and figure out what is its inverse. So let's say, once again, we have some point over here. We're going to go ahead and call P. Let's say that this is going to be my point of dilation then. So if I go ahead and draw OP over here and I extend it out, then let's say that P prime over here, that is going to be some point out here where my dilation is going to be a factor of K. Well, now I want to go backwards, so I want to move back to where P is going to be. So then that means I probably want to reduce that factor. So that means that the dilation inverse looks like it's going to be from from point O, and then it's going to be a dilation factor of 1 over K, because that will get me back to the same position, because K times 1 over K is equal to 1. Okay. All right. Now let's look at some coordinates using this whole, I guess, inverse thing to see how that actually works out. So first, what I'm going to do is we're going to go ahead and say we have two types of mapping over here. The first mapping is going to be a dilation. So that is going to be the first one, and I accidentally erased it. So that's going to be dilation of point O, which is the origin, and it's going to be a factor of -1. Then we also have another mapping, which is going to be the translation of x plus 4 and y minus 6. So that means we're moving to the right by 4 and then down by 6. The first example, what I want to do is I want to find out what is d squared going to be. Now, d squared in this case is the same thing as saying d product d, or d ought d. That's how we pronounce it in the last section, okay? So we're going to take a point and we're going to dilate it according to d first, and then whatever that result is, we're going to dilate it again according to d to see where that's going to go. Okay, so let's see. We're going to use this point F over here to see how dilation work. So here is going to be my point F, and I actually should have denoted that in this case. So so this is going to be for point F over here. Okay, so first let's do a dilation of -1. So we will go ahead and draw kind of like a line segment over here. Okay, so that's going to be OF right there. And if I go to the left, I'm going to go to the positive part. But if I go to the right, I'm going to go to the negative part. So it looks like then the first dilation, if I'm going to use O as my center, then that means that F is going to be translated to this point over here, and that's going to be F prime. So that's after the first dilation. Now, from there, I am going to do the same thing. Okay, I'm going to go ahead and apply the dilation again to a -1. So if I do that, then that means that F prime, well, we're going to go ahead and draw OF, and, OF prime. And then from there, if I am going to use a scale factor of -1, then it looks like it's going to take me back to F then as a result, because here at k is equal to 1, this is going to be k is equal to -1. So it looks like d squared in this case is going to be back to the point F then. So this is going to be -2, 4. So one would say, according to what we've been doing so far, d is supposed to be its own inverse then. So d, this dilation in this case anyways, is going to be its own inverse because it takes you back to the same point then. Okay, so that is going to be part 1 over here. Okay, number 2. This time I am going to do a translation, and I want to do the translation with the inverse, and we're still going to be using point F over here. So we're going to go ahead and first look at this point F, which is -2, 4. So let's go ahead and erase that part, okay? And let's see here. So erase that a little bit, and erase all of these guys. Okay. I want to solve for t inverse squared. Okay, so in this problem, I want to solve for t inverse squared, which is the same thing as saying t inverse ought t inverse. Okay, so then that means that I'm going to take the point F and I'm going to apply the t inverse for it. So if you look at the top right there, we're given that t is going to be for xy, translate to be x plus 4, y minus 6. So t inverse, according to what we said earlier, is going to be the translation of xy, which is going to be then x minus 4 and then comma y plus 6, because we're doing the opposite for the inverse then. So we're going to go ahead and throw that point into this mapping of t inverse. So I am going to move back by 4 for x, and then afterwards move up by 6. So that means that this is where it's going to take me then after the first translation. Then we're going to do it again because we're supposed to do it twice since it's squared. So we're going to go back by 4 again, and then we're going to go up by 6. So the result is going to be this point over here then, whatever that is. Looks like after the t inverse twice, the result is that it's going to take this point F and take it to the coordinate, which is going to be -10, comma, looks like if I'm adding correctly, looks like it's 16 then, okay? So there you go. That's the example for that one. Now, let's look at these two examples over here. This time I'm going to take a product of the two. I want to go ahead and find out what's going to happen to that point F then. So first, let's go ahead and get rid of these over here. Okay. Point F. First, what I'm going to do is I'm going to go ahead and translate it according to the translation that I have. So if I take point F and throw it into T, because again, remember, we're going from right to left. Okay, so going from right to left. Throw it into the translation. I am going to move over to the right by 4, and then I'm going to go down by 6. So over here, that's the point that we're going to get after we translate to T. Now I'm going to dilate it across, about the origin at -1. So there I will go ahead and draw a line through O and also that point that I just came up with. And if I'm going to the right, that's going to be in the positive direction. If I'm going to the left, I'm going to the negative direction. So then that means the end result is going to be over here then, because again, this right here is when k is equal to 1. So this is going to be when k is equal to -1. So the end result is that you're going to go to the point which is going to be -2, 2. Okay. Now let's go ahead and see if the product of D and then T is going to be the same thing, right? Because we said, if you remember the mapping, it doesn't necessarily give you the same result if you just kind of flip it. It's not commutative. That's what I'm saying. Okay, let's go ahead and flip that last one. Okay, so F, the first thing we're going to do is we are going to dilate it. So Let me go ahead and kind of remove all of this guy right here. Let me just kind of redraw it. So here's 0, 0. First, we're going to dilate it about 0. So here, we'll go ahead and draw the line that goes through it. So let's see. If I want the dilation, then the dilation is going to be over here at this point over there. Okay. Once I get that point, now I am going to translate it according to what's said. So the translation is going to be moved to the right by 4, and then we're going to go down by 6. So the result is going to be this point over here, which looks like it's going to be 6 comma negative 10. So that is going to be my end byproduct then. Okay. All right. Well, there you go. Thank you so much for watching. I will see you guys next time then. Have a good one.